Contour diagrams are analogous to the idea of a topographical map, which you may have seen before at some point in your life. This is a photo taken from a website of what's known as a raised relief map of the White Mountains in New Hampshire. If I actually had a physical copy of this in front of me, you would feel lots of bumps on this map, and where it's really bumpy, that would indicate some rugged terrain. And typically, a raised relief map is the type of thing you might mount on your wall, something like that. Of course, you really can't take something like this when you go hiking to find your way, because it just won't fit in your pocket. What you would probably take instead is what's known as a map like this, which shows the contour, elevation contours. So here's how this works. Each curve corresponds to a particular elevation. So for example, this curve corresponds to an elevation of 4,500 feet. So all the points located on this curve have that elevation. When I go from one curve to the next, on this particular map, there's an elevation change of 100 feet. So this curve has an elevation of 4,500. This would have an elevation of 4,400. Where the curves are close together, that indicates that the terrain is quite steep. So for example, let's take a look at what's happening here. Let's suppose I follow the Madison Gulf Trail. We can see that right in this area, the trail starts to get pretty steep because these curves are close together. In fact, if I go from here, 1, 2, 3, 4, there's a 400-foot gain in elevation just traveling along this little segment. As opposed to what's happening over here, let's take a look at the Buttress Trail right in this section. Because our path, the trail, stays between two successive contours, our elevation isn't really changing much at all. And so the fact is that we can take this map in our pocket. It's a two-dimensional rendition of this bumpy raised relief map. And that's the idea of a contour diagram. So if we have a function of two variables, x and y, the contour corresponding to a particular z value, c, is the set of all points in the xy plane satisfying f of xy equals c. Several contours plotted together yield what is known as a contour diagram, which is analogous to a topographical map, and it gives us a two-dimensional view of a surface formed by a function. So let's take a look at a particular function. This is f of xy equals x squared plus 6y squared. I plotted this graph, plotted the surface, and it kind of has a bowl-shaped look to it like this. And we want to get a two-dimensional rendition that conveys the information of this graph, and that's what a contour diagram does. So let's suppose we want to sketch the contour z equals 1. That means we're looking for all the ordered pairs x, y, so that x squared plus 6y squared equals our z value of 1. So 1 equals x squared plus 6y squared. Now it helps to know a little bit about conics. And in this case, this graph actually forms what's known as an ellipse. And the easiest way to graph an ellipse is to just look at its intercepts. To find the y-intercept, I set x to 0, in which case I'd get 1 equals 6y squared. Y would be plus or minus the square root of 1/6. To find the x-intercept, I would set y to 0, and I would get x squared equals 1, so x equals plus or minus 1. So those would be the intercepts of my ellipse, and if I graph the ellipse as a whole, it would look something like this. So the origin on in terms of my axes, my origin is right there. So this would be the contour z equals 1. It's an ellipse. Let's take a look at some more contours. For the same function, sketch the contour z equals 3, 0, and negative 1. Let's start with z equals 3. So now we set our z value to 3, and we get 3 equals x squared plus 6y squared. This also is an ellipse. So let's find the y-intercept. Let's set x to 0. 3 equals 6y squared, so y would be plus or minus the square root of 1/2. You can check that if you need to. The x-intercepts, set y to 0, so we would get 3 equals x squared, so x equals plus or minus 3. So those would give me the intercepts on the ellipse corresponding to this contour. We'll show you that in a moment. What about the contours z equals 0 and z equals negative 1? Suppose we set z to 0. we get 0 equals x squared plus 6y squared. Because both of these terms involve squares, the only way that this sum could equal 0 is if x and y were both simultaneously 0. If z is equal to -1, -1 equals x squared plus 6y squared, there's no values of x and y that will yield a solution to this because the right-hand side is greater than or equal to 0, but the left-hand side is negative. So here's the contour z equals 3. What I did is I plotted a few more contours. So here's the contour z equals 1. It consists of all the points on this ellipse. Z equals 2, all the points on that ellipse, and z equals 3, all the points on this outer ellipse. And z equals 0 is just the point at the origin, which is right there. So in terms of our topographical map, we can see that when I go from this point in the xy plane towards a point up here, my elevation is increasing from 0 to 1. As I move from here to there, my elevation is increasing from 1 to 2. If I move from here to there, my elevation is increasing from 1 to 3. Likewise, if I go from here to there, my elevation is increasing from 1 to 3. But because the contours are closer together here, the surface would be steeper here than it would be over here where the contours are further apart. I plotted this on Mathematica as well, which has a nice option for graphing various contours. Unfortunately, it doesn't label the contour at the origin, but this is what I get. It does a nice job of coloring. Now here are a few things to keep in mind. The axes of a contour diagram are always labeled in terms of the two input variables, which are x and y in this case. Notice I've labeled my axes x and y. The output, the z value in each case, should be indicated next to each contour. Notice how I've labeled the z value next to each contour. Different contours never cross. For example, if the contour z equals 1 crossed z equals 2, that would indicate an ordered pair xy that yielded two outputs, and then we would not have a function. The difference between successive output values should be the same on the diagram so as not to give a misleading view of the surface. In this particular case, the change in z was always 1 when I went from one contour to the next. Let's take a look at another example. Sketch the contour diagram for z equals f of xy equals y e to the negative x, and we're going to look at the contours 2, 1, 0, -1, and -2. So let's set z to 2. So we set 2 equal to y e to the minus yx, and we want to determine what this graph looks like. Now, if you wanted to graph on a calculator, entering something like this would be pretty hard. So if you can, it really helps to be able to solve this equation for y. If I multiply each side by e to the x, I would have 2e to the x here, and the exponentials would cancel here. So I'd have y equals 2e to the x. This is our familiar exponential graph that's been stretched by a factor of 2. That's pretty easy to graph. If z is 1, we could do the same sort of thing. 1 equals y e to the negative x. So y equals e to the x. That's easy to graph too. If we wanted z equals -1, we would set -1 equal to y e to the negative x. Multiplying each side by e to the x would give us minus e to the x equals y. So that's going to be this graph, except it's going to be reflected about the horizontal axis. Z equals -2. -2 equals y e to the negative x. Solving for y gives y equals -2 e to the x. So that would be the graph of e to the x stretched by a factor of 2 and then reflected about the horizontal axis. Finally, let's take a look at the contour when z is 0. In this case, I set 0 equals y e to the negative x. This exponential will never be 0. So this equation is 0 whenever y is 0, and that's going to be a horizontal line. So this example shows, among other things, how one tool for graphing contours is if you can solve your equation that you're looking at for y, that's going to be easier to graph. Sometimes your contours might consist of curves. For example, our contour diagram is going to have an exponential graph, but it's also going to have a horizontal line y equals 0. Here's what it looks like. This is the contour z equals 2. It's the graph of y equals e to the 2x. This is the graph z equals 1, y e to the x. This is z equals -1. There's a missing negative sign. This curve is z equals -2. And we saw that if z was 0, the contour was y equals 0. So let's check things. Have I labeled my axes? No, I haven't. So label that axis x, label that axis y. Again, the origin is right here on my graph. I've labeled all my contours, and the change in contours between one contour and the next is delta z equals 1 in this case. Another example. F of xy equals y squared minus x squared, and we want to look at the contours 0, 1, 2, -1, and -2. Now this is, when I look at 1, I get 1 equals 1 y squared minus x squared. This is a hyperbola. In general, if you have a number times y squared plus or minus a number times x squared equals 1 or something like that, you have a hyperbola. So this is another example of a conic. So hyperbolas kind of have this shape or have this shape depending upon where the negative signs are in our formula. The easiest way to graph a hyperbola is again to look at the intercepts. Let's suppose I look for the y-intercepts. I set x equal to 0 above. That gives me 1 equals y squared, so y equals plus or minus 1. Those would be the two y-intercepts. The x-intercepts are found by setting y to 0, in which case I'd get 1 equals -x squared. That doesn't have any solution. So in this case, the y-intercepts would be plus or minus 1. There would be no x-intercepts. So chances are we're going to get a graph looking like this as opposed to a graph looking like that. Z equals -2. -2 equals y squared minus x squared. Y-intercept, set x to 0. -2 equals y squared. That has no solution. The x-intercept, we set y to 0. We get -2 equals -x squared, so x equals plus or minus √2. So in this case, when z is -2, there is no y-intercept, but there are two x-intercepts, which the origin is right here in each case, would suggest that the contour z equals -2 corresponds to that graph. Again, this contour has two x-intercepts, no y-intercept, so it's going to look something like this, whereas z equals 1 has no x-intercepts but two y-intercepts, which means the graph would basically look like this if this is the location of the origin. Let's take a look at the contour z equals 0. This one is a little bit different. 0 equals y squared minus x squared. So what does the graph of this look like? Well, we can factor this because it's the difference of two squares. Y minus x times y plus x is 0. So let's set each of these to 0. I get y equals x. That's a line, the 45-degree line. I get y equals -x. That's also a line. It's the 45-degree line, except it's oriented sloping downwards. So now we have two lines that make up a single contour, and that is sometimes the case, that two curves can comprise a single contour. So here's what we have. The contour z equals 0 corresponds to this line, which is y equals x. Also, it includes the line y equals -x. The contour z equals -1 consists of both branches of this hyperbola, which I've drawn in red. Z equals 2 corresponds to both branches of these hyperbolas, which I've drawn in green. Notice how, whoopsie, I haven't labeled my axes, so let's label our axes, x and y. So this is the contour diagram for x squared minus y squared. So what does this tell us? Suppose we were standing on the surface. When x is 0 and y is 0, our elevation is 0. If I move north, my elevation is going to increase to 1 and then 2 and then larger values. That indicates that I would be going uphill on the surface. On the other hand, if I moved in this direction, if I moved, I guess this would be east, from here to there, my elevation is becoming negative. I'm going downhill, so to speak. Finally, if I was at the origin and if I traveled along this 45-degree line, my z value would stay at 0, so my elevation would remain unchanged. Here's some examples for you to consider in preparation for class. So we have a function f of xy equals 2x plus y. Sketch the contours corresponding to these values. Sketch the contour diagram for f of xy equals x squared consisting of these contours. In this case, we're going to have circles. Sketch the contour diagram for f of xy equals yx consisting of these contours. And the same thing now using sine of x minus y consisting of these three contours. Now I should point out that number 2, you're going to have circles. But for numbers 1, 3, and 4, you should be able to solve, when you graph each contour, you should be able to solve for y. So do this in preparation for the next class.